Today we continue studying homomorphisms and kernels and so on. And so this is lecture 3.5, and we will talk about factor groups. So before introducing this very important and beautiful idea, let me start with reminding you where we were. So let's suppose that G is some group and that N is a normal subgroup. So as we already discussed, there is a natural source of normal subgroups. Normal subgroups appear as kernels of homomorphisms. So if you have G, a homomorphism to G prime, which is denoted by F. F is a homomorphism, doesn't matter, it's injective, surjective, or neither, then kernel of F is a normal subgroup in G. And this is how we denote normal subgroups. Okay, so, and as I already tried to explain, so the reason why we like so much normal subgroups and why we like so much kernels of homomorphisms is because the subgroups are, in some sense, they don't depend on how you denote your elements in your group. So if you apply these conjugations, inner automorphisms, these normal subgroups stay fixed, and other subgroups get permuted between each other. And so you can think of these normal subgroups as sort of arising from nature. So if you have Sn, there exists a unique homomorphism to S2 called sine. Its kernel is a very important normal subgroup of Sn, even permutations. But if you take a subgroup of, say, all permutations fixing n, that's a subgroup, but it's not normal, and intuitively this is because to even define it you need to choose some particular element n in your set, and if you apply conjugation, such subgroups fixing one element will be permuted. So this is why they are so important, and this is why they appear all the time. So when we'll see groups coming from symmetries, normal subgroups will usually be groups which you can define by some geometric properties. You can give them kind of geometric description. And so now I want to formulate the main result of this lecture. So that's a proposition. So if N is a normal subgroup of G, then there exists a homomorphism from G to G prime, F, such that kernel of F equals to N. And notice this equals. It's not isomorphic. It is indeed a subgroup of G, which is the same as this N. So, so this is the theorem. And next, in the next lecture, I will explain why basically such homomorphism is in some sense unique. Okay, so proof is of course by construction. So for every group G and N, I need to find a new group G prime. Okay, let's look at what this G prime might look like. So let's first analyze the picture. So let's suppose we have my group G, and we have this G prime constructed, and then we have this homomorphism. So this is N, and we know that it is supposed to go to identity element. Okay, so what about other elements in G? So if you take, so this is homomorphism F. If you take some other element, it will go to F of G, somewhere here. And then it's easy to see that for every element X inside the whole class Gn, F of X is equal to F of G. I mean, because F of X equals to F of G times some element N in N, which is equal to F of G, F of N, and the second one is identity here. So this is E. So that's the same thing. Let me try to make it slightly more. Okay, that looks strange. Okay, so this Y, we know that actually the whole class Gn goes to element f of g, and so on. So basically the idea is that if you think about, there is a subgroup here which is the image, and of course we don't care about anything else actually. So basically elements in the image are all coming from different conjugacy classes, sorry, different cosets of G relative to n. And you can ask left cosets or right cosets, but n is normal, so thankfully they are the same. And so now I am trying to do the whole picture backwards. So I have this G and I have a normal subgroup, and I need to construct somewhere to send G. And the idea is to define this G prime as a set of cosets. So definition, so maybe let me say construction. So construction. So I'm constructing a group G prime, which is called factor group. And factor comes from the idea that our equivalence relation factorizes the set. And it is denoted by G divided by n. And as I said, it is just set of cosets Gn. So we have all these cosets for every element, and the set of cosets is called the factor group. So these guys, these are elements there. And in particular, yeah. And then the question is how to multiply them. What is the group structure? So define. So we have already defined this group as a set. So define, and let me denote it by G in brackets. Define product by, and then you know if you want to multiply two elements here, which are two cosets, say G1, G2. Of course, you know that G1 will go to some element f of G1, G2 to f of G2, product will go to product. So it's very clear that we should multiply cosets by saying that when we multiply G1, which I remind you is the same as G1n, on G2, which I remind you is G2n, and I just put it equal to G1, G2 coset, which is G1, G2, n. And this is just dictated by this idea that we want to multiply our elements exactly like we multiply elements in the image. So two cosets will go to the coset of the product. So that's all very good, except as usual, when you do multiplication like that, so you have two classes, so subsets of your group, and you are trying to say what happens when you multiply elements there, and you say just take any, multiply them. The question is why it does not depend on the choice. So the first thing to check is what's called correctness. Okay, so let's prove correctness of the multiplication. So what it means? So correctness so if G1 prime class equals to G1 double prime, then the class of G1 prime G2 equals to the class of G1 double prime G2. So what this means, it means that if you change this element by another element in the same class and multiply them, you will get elements in the same class. And this is not true if your subgroup is not normal. It's a very crucial property for normal subgroups. So you'll see where I'm going to use it. So let me prove it. So proof is very simple when you know what to prove. So you know that the classes are equal, and what it means that there exists n in our subgroup such that G1, let's see, G1 double prime equals G1 prime times n. And so now G1 prime G2 will equal to G1 double prime G2 will equal to G1 prime n G2. And now n G2 G2 inverse lies inside n. And the reason is because this is an n and n is normal. So because n is normal. And since this is true, it means that this equals to some another n prime in n. And what we get that n G2 equals to G2 n prime. But then we can easily see that G1 prime, then G1 prime, double prime G2 equals to G1 prime n G2, and n G2 is G2 n prime equals to G1 prime G2 n prime. And so what it means that these two elements are in the same coset, because if you take this inverse times this, you get n prime in n. And this class of G1 prime G2 equals to the class of G1 double prime G2. So this is why the definition is well defined, and so what it means, we got indeed an operation from the set of classes times the set of classes to the set of classes. And hopefully you already kind of understood that the simplest example of this construction will be integers modulo n, and that's exactly how we define addition of integers modulo some integer. Okay, so this defines a structure of a set with operation which is well defined, and then of course we need to check axioms, and axioms are simple. So now you can just assume that this is a formula, and so for associativity you just take G1 G2 times G3, and this equals to G1 G2 class times G3, which equals to G1 G2 G3, and then of course you can rewrite it in different order, so that's not surprising. Okay, so identity is obviously, so identity in our group G prime is of course the class of the unit, and the class of the unit is n. So it's a class containing unit, but also it's the same thing as n. So the subgroup itself is identity in the factor group. That's kind of interesting. And of course the class of G inverse is the class of G inverse. And let me not check the axioms, they are super simple. So this construction, the construction of a factor group, again, it is defined just because the group is normal. So if you don't know that the group is normal, you cannot use this trick. And so there is no way you will exchange the order in products like G1 prime and G2. So you will never make it G1 prime G2 n. That's the problem. So for n to jump over G2, you need to use this normality. And this is a very important construction. So every group, normal subgroup, you get a factor group. And now we want to show that there is a homomorphism from G to G factored over n, and the kernel is n. Let me do it. Okay, so next, so let me construct, so there exists a canonical homomorphism from G to G factored over n. Let me denote it by P. So this is a group. This is a group of classes. And canonical, so firstly, I will construct this P in a second, it's very simple. And canonical, of course, is a word which is not completely well defined in mathematics. It appears all the time. And its meaning is that I will write down a formula for P, which doesn't depend on any choices. So there is kind of one nature-given map like that. And there are various ways to make this canonical word mean something, but maybe I'm not going to talk about them now, though we might do it next quarter a little bit. So what is this homomorphism? So homomorphism is very simple. So P takes element G and just sends this to the class containing this element. So, you have this decomposition into classes. This is N, this is Gn, whatever cosets we have. Every element just goes to the corresponding coset as an element here. And so P is surjective. That's trivial, just because every coset comes from some element. Also, P of G1, G2 is of course the class of G1, G2 just by definition, but that's the same as the class of G1, G2, which means that this is P of G1, P of G2, and miraculously we got, actually not very miraculously, that P is a homomorphism. Homomorphism. Okay. So it is a homomorphism, and finally we can look at the kernel. So surjective homomorphism and kernel of P, you can guess what it is. So this is a set of elements G such that P of G is identity, and this means it's N as an element class of identity. But P of G is an N. P just sends every element to its coset, so it is just N. Set of elements G such that they are in N. And thus we get that the kernel is N. So every normal group, N is normal in G, then N is a kernel of a surjective homomorphism from G to G over N, which I denoted by P. That's it. Okay. So I proved for you almost everything here. And next lecture we will talk about some So first, next lecture I want to talk about examples, and there are lots of beautiful examples. And after that, we'll talk about different theorems related to that. Actually, let me talk about examples right now. So there are not so many, we'll see much more later on. So examples. Okay. So the first one, probably the first kind of classical example of a factor group construction you know from elementary school. You take Z as a subgroup, and you take 2Z, that's just notation for even numbers, 0, 2, as a subgroup. So Z is abelian, so it's normal subgroup. And so if we are working with abelian groups, you can factor anything over anything. There are no restrictions, nothing to worry about. So Z over 2Z is a factor group. And it has two elements, which are two classes, and one of them is denoted by even, the other is denoted by odd numbers. And if you want to add two numbers, two classes, you just add any two representatives and see whether it's even or odd. So that's very, we have seen that so many times during this class. So that's not a big surprise. And of course, if you take just nz, all integers divisible by n, it's a normal subgroup of z. And so z over nz is a factor group. Factor group. So this is cyclic group of order n we discussed so many times. We will return to it very soon when we talk about abelian groups in general. So, okay. So that's one example. What is another example? So second example, we have a n being a normal subgroup over Sn. And like here, there are two classes of permutations, even, odd. And so what it means that the factor group contains just two classes, two cosets. And so it is isomorphic to Z over 2Z because there is just one group with two elements. And elements there are even permutations and odd permutations. And homomorphism, which is P, this is just sign. So P here is just sign. Okay, let's continue. Okay, so more examples. So let's recall this S4 example. So we had S4, and as we discussed, S4 has just four normal subgroups: identity, the whole group, A3, and finally this Klein's group, V4. And the question is, what is the factor group? And actually, you can take this S4, and you have this homomorphism with kernel to V4, and this is a homomorphism to S3, and this is surjective. So actually, S3 is isomorphic to the factor group S4 over V4. And how to think about it? So the easiest way is probably to think geometrically. So if you take a tetrahedron, as we discussed in class, I guess, you can have a tetrahedron with 4 vertices. Imagine it's regular. And then there are S4 different isometries of the whole space, which send tetrahedron to itself, like rotations, symmetries, and so on. And so there are these 3 pairs of opposite diagonals. And so this homomorphism sends S4 to the element in S4 to the corresponding permutation of 3 pairs of opposite diagonals, or you can think of it as like diagonals connecting mids of edges. And basically, that's your map P in this case. So kernel consists of those transformations which fix these pairs, and so they have to exchange either 1, 2 with n3, 4, or 1, 4, and 2, 3, or 1, 3, and 2, 4, or be trivial. So this is V4, which is a kernel. And actually, in the next lecture, we'll prove that if you have any surjective homomorphism, then the factor group is isomorphic to the image. Okay, finally, example number 4. So let me take GLN over some field, and inside I have these matrices, which are this kind of diagonal, so lambda, 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 0, 0, where lambda is inside F without 0, multiplicative group. So we know that this thing is actually the center of GLN of F. Matrix commuting with everything. So it is a normal subgroup. So there is a normal subgroup F multiplicative group of a field inside GLN of F. Fine. So for every 2 groups, if you have a normal subgroup, you can look at factor group, GLN of F factored over F cross. And this is, you can try to think what is this group, but actually it's not so simple. So this is some group which deserves a name. It's called PGLN of F. We will talk about it later on. And F cross, and what it means, these are kind of matrices, invertible matrices up to up to multiplying on a constant, multiplying on lambda not equal to 0. So basically you have a matrix 1, 2, 3, 4, and in the factor group it's the same matrix as 2, 4, 6, 8, which is the same matrix as 1/2, 1, 3/2, 2. So working in a factor group, it's like working with integers modulo something. The same element can be represented by different particular matrices. So we will see later on this geometric meaning of PGLN of F, and we will talk quite a lot about it. Okay, so this is everything I wanted to say in this lecture, and in the next lecture I want to discuss a few more kind of high-end facts about factor groups and discuss basically uniqueness of this construction.